day 724 off the grid, and today is going to be quite a big solar day. I have here on my workbench the boost amplifier or current amplifier, whatever you want to call it, repeater, DC repeater, whatever it is, that I use with the Morningstar on the lighting circuit, the flooded L12 battery circuit, I guess the B batteries. So I've noticed over the last couple of days those batteries haven't been charging up that well, you know. I notice these things pretty quickly, you know. This is the unit. You've seen it in my other videos in the power room. So in the end I traced the fault to this unit, not to the shitty car audio fuse that has caused problems before on that circuit, which I am going to replace as a matter of course while doing this, I've decided, because it doesn't look so good. I'll show that later. But the main thing was, what was wrong with this? Did I pop a transistor? What happened to it? Well, whipping off the back, it was very easy to see what's gone on here. These here are the emitter resistors, and the reason why I've got emitter resistors is because there's two bipolar transistors in parallel, and unlike MOSFETs, they don't tend to like sharing current evenly unless you introduce an external resistance to even up the current flow. And what I used was open wire resistors made from bits of heavy guitar string. I think this is a 56 gauge B string, you know, the kind of string you'd use to play death metal on the low string of the guitar. They're made from a combination of steel and nickel, so they exhibit quite a good positive temperature coefficient. But unfortunately, it would seem, made of those materials, if they run too hot for too long, eventually they decay, and as you can see, they've sort of parted. Sorry, no macro again. Much like a fuse, so they weren't this far apart when I opened it up. They were just broken like that, but this has interrupted the current flow. They've both done it. It would have been a cascading effect. One would have gone and then all the current would have gone on the other one, and it would have gone pretty quickly. I don't know, within moments. It could have been within days of each other, even a week, I don't know. It's obviously not a major catastrophic break, it's just slow degradation of the materials, so I've got to replace them. Of course, the big question now is what to replace them with. I could get some more B string and stick it in there, but obviously in another couple of years I'm going to have the same problem, and I'd rather not. So we've got to come up with something that serves as an emitter resistor, and it's not going to suffer the same issue. And it's got to be extremely low resistance, because we're talking current of, you know, several tens of amps that can flow through this, so we don't want something like half an ohm or something like that. It's going to cause a massive voltage drop. It doesn't have to be very big at all, it just has to have some resistance. The positive temperature coefficient of these was nice, because it means that as more current flows, the resistance actually gets a bit higher, and it actually helps resist more, but it's probably not, you know, 100% necessary. So I've got to come up with a solution for this, and providing none of these devices have actually failed, I'll do a quick check of those. I'll put it back together. And now I'm basically done. I've just got to case it up and take it back in the solar shed. I haven't done any bench testing, but I'm pretty confident it's going to work. I have checked the transistors actually to make sure that they're all okay and they're fine. So what I've done is replaced those open wire resistors made from the guitar string with these 30 amp automotive fuses, blade fuses. I'm actually still using these fuses as resistors because these have quite a lot of resistance. No wonder when you look at the actual fuse element in there, it's very, very tiny. I mean, all fuses offer resistance, so these actually effectively continue to work as extremely low value resistors, and it's exactly what I need. And of course they will also function as fuses as a last line of defense if something really went wrong, because all this wiring in here can handle the 30 amps or whatever, 60 amps or whatever short term that's going to blow these things. So yeah, so now they're dual purpose. They're mainly installed in there as extremely low value resistors, but they will also perform their intended function as fuses if necessary. So I guess it's a little bit safer, isn't it? Same over the other side. Now you might notice that there's less clutter in there if you watch the first part of this video quite closely. Well, for one thing, I've redone the wiring to the LED. Formerly there was a solar garden light circuit wired basically straight across this 10 ohm resistor here, and when the voltage of this developed enough, that solar garden light circuit would turn on the LED. But obviously at some point too much voltage developed across this and the LED got fried, so not a great approach there. So I've removed that, but thought, you know, I kind of want an LED doing something on here, so instead I've gone for a much simpler arrangement. The LED is effectively wired between these two terminals here. That's the solar input, that's the battery output. So the LED is wired straight across those two terminals, with a current limiting resistor of course. And the idea is whenever there's a decent potential between those terminals, the LED will turn on and start to glow. Especially during phases when regulation is starting to happen and things like that. There may be enough potential across there for it to turn on all the time. But cleverly, and this is the resistor that feeds it, I've wired the negative side of it to the battery side of this fuse, so it also functions as a blown fuse indicator, because obviously these are buried inside the guts of this device. So if this LED normally works, I really don't know what its behaviour is going to be until I try it. That's the funny thing about it. But if this LED is normally on and one day I see it off, I'll know straight away that it's because this fuse has popped, or something similar. So that's basically it really. Simplified the LED wiring. I also removed that terminal block that was down the side and replaced it with this binding post, because I only need one extra connection. This is the connection which connects the control voltage from the Morning Star through to this unit. And incidentally, of course, the Morning Star is not modified in any way to provide that control voltage. I take it directly from the solar input of the Morning Star. Interestingly, this circuit does not have any connections to ground whatsoever. All the potential in here that's developed for its operation comes from the difference between the solar input and the battery output, and that's all the voltage that it needs to run off, so therefore it doesn't need a connection to ground to take power. The reason why I had this, here it is, well, this was originally part of this unit when it housed the equipment that was in its former life, but I was using this originally because it was the way I was connecting up the extra panels to the Morning Star, but I'm changing that now and tidying it up, so that's become redundant, so I just thought I'd remove it, which also removed a couple of bypass wires that were inside there, which were sort of adding to the mess in there. Now this is where it gets to the point where it's really awesome to be able to build your own stuff. You know, I mean, this is a very simple circuit. I mean, there's literally 3 transistors, one under there on the heat sinks, and the transistor which drives them there, and 1 resistor. Well, I guess these are counted as resistors too. So 3 transistors, 3 resistors, 4 if you count the LED's resistor, but that's kind of you know, it's a bell and a whistle. It's not really part of the main operation. Yeah, the nice thing about building things yourself like this and keeping it simple is that if something goes wrong with it, you can quickly troubleshoot it. You don't have to rip it out and anxiously send it off to the man and do without it while you're waiting for what could be an expensive repair if it's not under warranty or anything. I'm kind of chuffed when I make stuff and something goes wrong and I can just fix it. Of course, a big company like Midnight Solar or something like that wouldn't decide to use something as experimental as a guitar string to function as an open wire resistor. So that's the other side of things, isn't it? But when you make something, if you make something and you don't get something quite right, you can go back to it and improve it, which I think I've done here. The only drawback, of course, is if you make something for someone else. That's the problem with homemade stuff, is that when you make it yourself, something goes wrong, you kind of already know what it might be, or you quickly find out and you just go and fix it. It's no biggie. Trouble is when you make things for other people and something goes wrong with it, often they don't actually get back to you and go, hey, this was going real well, but then this happened. They'll just discard it thinking, oh, it's fucked. Just like everyone does with cheap commercial equipment. But homemade stuff can be fixed quite easily. Sometimes it's a genuine fault, sometimes it's just a design fault that needs to be rectified, because this is the final unit and this is the prototype. You know, I didn't build up a whole lot of these and put them through torture testing or anything. I built one of them. In fact, I may not even have a written schematic for this. I probably designed it with the soldering iron, so to speak. But nevertheless, it should be all hunky-dory now, so I'll go and install it back in the solar shed, and if I've got time today I will work on something else that I was going to actually do in the solar shed, which is to work on that timer and the relay control for that. This was kind of a bit impromptu, but when you're off the grid, it's the kind of thing you got to do. You got to roll with it. When things need fixing, you know, fix them. So there we go. That'll do for now. And of course, here we have it reinstalled in the power room. The big boost circuit. I don't know what you'd really call it. It's like a slave controller, I guess, but it doesn't do any sensing itself. It just follows what the Morningstar does. I built a few of these in different ways, but this is the one built using bipolar transistors. Looks good back up there. I've done a bit of rewiring, of course. This used to be fed through the terminal block on the unit itself. Now this just goes directly to the brown wire, which connects to the 70-watt solar panel. This is just temporary until I do a bit of tidying up here. I'm going to be doing away with this nasty car audio fuse here. These things are really shocking. In fact, this end has actually got so warm it's actually melted itself in. You can't take that end out. You can unscrew the outside plastic, but you can't remove the inner fuse socket thingy. Pretty bad, eh? Pretty bad. I would trust on a 12 volt high current DC circuit a 230 volt AC rated circuit breaker any day rather than these. Any day. But that's just me. Anyway, so there's the connection for the signal, and as you can see, it's a bit clearer now than it used to be. You can see how it works. That's connected directly to the solar positive on the Morningstar. So this is functioning as two things. It's the input, obviously, for the 70-watt solar panel after it goes through this silly old ammeter, but it's also the output for the signal which drives this. Now, how can it be an input and output at the same time? Well, of course, the funny thing is that the voltages only flow in one direction, from the solar panel into the Morningstar and out of the Morningstar into the battery. Same here, the voltage flows out of this terminal into the Morningstar and towards the battery. So that's how it works. Whenever the MOSFET in the Morningstar turns on, like it is at the moment, it basically connects this to a lower potential than the solar panels, thus turning on the whole unit and allowing this 8 amps to flow at the moment, even on this cloudy day, which isn't bad, but these batteries are kind of thirsty. Although this can get a lot higher on a sunny morning when the lights have been used. So that's what it basically does. Power flows out of this wire in through the Morningstar into the battery. When the Morningstar gets to the point where it starts PWMing, switching its MOSFET on and off, the signal gets switched on and off too, and these transistors switch on and off at the same time as the Morningstar, thus modulating this far bigger amount of power which is currently coming in through here. So that part of the power goes into the box and out of the box and through this another shitty car audio fuse, but at least this one's a new one when I got it, which may explain why it hasn't melted up yet, into the batteries. None of that high current goes anywhere near the Morningstar, only the control current, which is, I don't know, in the order of maybe tens of milliamps, maybe getting up to low hundreds of milliamps, but it's not very high. That's all that flows through it. So yeah, while we're looking at this time has been utterly successful. Sorry Adam, I haven't really had the impetus to develop this further and start throwing Arduinos at it, because this has done the job really well. It just, at about, I think it's 11 o'clock, no, it must be 12 because it hasn't come on yet. This time is accurate now because it's daylight savings. The relay will come on and this short out this diode and allow the Morningstar to operate on a lower voltage potential. Come 5 o'clock it will open again and this diode will become in circuit and everything will float up by about 0.6 volts, which is what I want it to do, and it's doing it very, very nicely. I do have plans for Arduino, but for something different now. It's just a matter of finding the time to do it. And I've said it before, for me, usually finding an analog solution to a problem is a lot quicker because it's something that I'm really familiar with. It's something that I've played around with since I was a little kid, you know, so it's something that comes natural to me to do it with an analog solution. And usually I don't have much time to muck around with things just for the sake of mucking around with things, so I'm usually after an end result as fast as possible, which is a bit unfortunate because I would really like to do the whole Arduino thing. But anyway, this is working now. I need to get on replacing this fuse as soon as practicable, and I guess I can reinstate the battery balancer circuit, which is down here, which has been working really, really well. In fact, the reason why it's been working too well almost in the last few days is because of the lack of current coming from the main charging, but we'll see how that fares now once the current has returned from this stuff. But that looks like mischief managed for now, so I better go and get some breakfast on and have another cup of coffee, I think. Well, it's been a pretty shitty morning for sun, but it's now, yeah, that's the right time, in the afternoon, and the sun's coming out a little bit, so things are really starting to rev up here. As you can see, the relay's now activated, so this will be clamped to around 14.5 volts that it can get up to a maximum at the moment, that the Morningstar will regulate it to. But look, we're getting some good amps, 16, 17. The sun came out quite bright for a few seconds, 3 or 4 or 5 minutes ago, and I saw 26 amps on that meter. You know, this will handle it no problem. Each of these transistors, which are 2N3771s, will actually handle 30 amps a piece. They are pretty grunty. So at the moment they're sharing about 8 amps each, and I can feel by their temperatures is that they're about both the same temperature, so those fuses that I installed in there are helping to share the current. Now the LED is not on because I measured the voltage between the input and the output, and even with 16 amps flowing, it's only about 1 volt, and of course you need at least 2 volts forward going voltage across a red LED before it'll light. Although I have seen it flash briefly on and off every time the PWM briefly disconnects, which these charge controllers do now and then. So I'm pretty pleased, yeah. So we're getting about 1 volt drop across here, which is not bad for a bipolar setup. Of course you do a lot better with MOSFETs, but hey, that's okay. We're getting 250 millivolts dropped across this fuse. Now that is not acceptable because a fuse should drop practically 0 volts. It's always going to drop some, but that's not good enough for me. If you do the maths, 250 millivolts at say 16 amps going through it,
that's about 4 watts. And although I'm quite happy to let 4 watts float away in other parts of the system, not in a fuse holder. So that's going to go away. I mean, 4 watts has obviously been enough, it's produced enough heat to sort of plastic weld this end, well not the cap but the fuse container contacts inside the plastic, you know, like I said before. Not good, not good. But overall though, yeah, that was a good repair this morning. It looks a bit neater and tidier here. Of course I couldn't help but use a bit of ancient fabric coated cable. In fact, it's actually inside, it's cotton insulation, there's no rubber or anything in that cable. I think it would have been formerly wiring that may have been used in automobiles back in the day. I just got a length of it once and I kind of like that kind of stuff. Kind of like fabric covered cable. So I use it wherever I can. But there we go, 15 amps, 14 amps, you know. The day's not the most spectacular out there, but oh, don't know if you caught that, but we just had a quick flash from the LED, which would have meant the Morning Star briefly just interrupted the output like it does now and then. So yeah, I'm pretty pleased with the morning's work, you know. Look at these amps, people! You know, all these bragging people, over their solar setups. Well, I'm just trying to show you what's happening here, basically, you know. I've actually done something today, so it's worth showing, isn't it? And yeah, I reckon I'll be doing a little bit more this afternoon, so this could end up quite a long video. And here's the beginnings of the second part of today's effort with the solar setup. We have here a rather chunky relay in a nice plastic case. Here's the lid for it. This is the relay that's going to be switched by the timer that I've modified to be a countdown timer, as you saw in the previous video. This one here has a coil resistance of 3400 ohms, so it's designed for 230 volts AC, so it's got an AC coil. The contacts are rated at 15 amps each at 230 volts AC, so they'll be good for about that on 12 volts DC, no problem. There's 2 sets of contacts. It's basically on off, there's no, you know, it's not a dual throw switch, so it's on or off. That's all I need, because all it's going to be doing is connecting the output from the 10 volt battery bank to the input of the boost converter, which steps up the voltage and allows it to charge the 24 volt fridge bank. I've chosen to wire these 2 contacts in parallel. I could have either just used one set, wired them in series if I was worried about the DC braking thing, but I'm not. Or, as I've done, wired them in parallel to sort of increase the contact life, so they're not each taking the full brunt of the current, which is going to be between about, it's going to begin about 14 amps and it's going to sort of finish off about 7 when it's finally actually doing the braking, so it's not a big challenge for this relay. I've wired them in parallel, but not very well. I just used the existing wires that were already in the case, so it's got some really heavy ones on one side and some significantly lighter ones on the other, so the contacts aren't going to share the current equally, but who gives a fuck? As long as one set of contacts is not taking all the current, I'm happy enough with that. And because I'm switching DC across a relay, I have taken the expedience of wiring this capacitor here. This is a 0.3 microfarad, it's an X2 capacitor, but that's probably overkill. But it had all these wires already sort of sticking out there, so that made it quite easy to wire in. And yeah, it's got a bleeder resistor still across it, but that's like half a meg, so again, who gives a toss? I should have strictly cut it out, but it doesn't really matter. So this is wired across the contacts, so that the moment the contacts open, this capacitor will be discharged and it'll take just a little bit of the current that's still flowing away from the contacts, thus allowing them to open with lesser opportunity for arcs to form. And it does really work well. Ideally, you'd probably want a bigger capacitor than that. I would use at least a 1 microfarad, sometimes even bigger. Like if I know a relay is going to be switching like DC quite often, I'll put something like a 6 microfarad fluorescent light capacitor across there. You don't want electrolytic, you want a non-polarized capacitor, because electrodes can be a bit slow to fill. But this is what I can fit inside here, so it'll afford some protection to the contacts. So that's basically that, really. We've wired up the relay. This is the main side where these blue wires come in. They are total overkill for the coil current. I don't know who put this together originally, but you know, that's it really. Yeah, I'm going to go and install it in the shed. Oh, looks like the sun's come out a bit. Oh, I better go and check the current on the new circuit for the B-bank. And here we have the relay in situ in the power room. I haven't put the low voltage wiring in yet, or put the case on obviously, but I thought you might like to see it operate. So here we go. Relay on, relay off. Relay on, relay off. Yay. Well, obviously it works, so let's get on with it, shall we? So here's the relay box complete. It's on the wall, it's cased up. I've fitted this lovely old fabric covered lead. This is an original, not a modern reproduction. And it runs down to the plug that's got, of course, the previously mentioned modified timer. So what I've actually done is set 2 patches of 10 hours, one in the 12-hour part of the time and one in the 24-hour part of the time, because that way I only need to click it forwards a little bit each time to get my next 10 hours. I don't have to wrench the dial all the way around. Of course, I can wind it in a bit further if I just want 5 hours or something like that. So it's a pretty sweet setup, really. Yes, I mounted this blue plug box on the wall the other day, and it runs from the power jack there, 1500 watt pure sine wave inverter, off the 24 volt circuit. I was starting to get a pile up of tap on plugs here, and it was a bit unsightly, and I wasn't going to make a video about, oh look, Zan mounted up a plug box. That would be stupid. But one thing I did do, see here how it's mounted, I actually screwed in some little metal straps into the back of it using a really short screw so it didn't go through and short circuit on anything. Because those keyhole slots that these things all have to mount them on the wall are just hopeless. You never get the screws aligned right. They fall off every time you put a plug in or take a plug out. But with this mounting, she's on there robust. Yeah, a lot of the old school plug boxes, like the old Carltons and stuff I had a bracket which came out like that. You know, oh, you can see the screw, but for me, I'd rather see a screw than have a nightmare trying to set it up so it's hidden. But yeah, there's my circuit. So basically powers the boost converter here. I can't test it at the moment because these batteries here are so fully charged that it's gone into regulation mode. This red LED tells me that, so the boost converter wouldn't work even if I turned it on. Wouldn't do any boost converting, so I'm going to have to wait till this evening when the sun goes and I can give it a try, but I'm pretty certain it'll work. And I've tested that the relay works, the coil and the contacts of course, and all I've done is added this extra wire here and put a relay switch in, so can't be any much different, can it? So that's basically it then. On day 724 off the grid. Well, just when you thought the story ended, well, it didn't. Just after I finished filming the new relay setup, I was looking over at this and I was expecting the LED to be on because it's been coming on when it regulates now, but it wasn't. And I thought, oh no, has something failed in this already after I've just worked on it today? No, it hadn't. I quickly realised it was the fuse that was up there had decided to go kaput. Not the fuse itself, but the fuse holder. Because when I shoved in a multimeter probe to check if there was some decent voltage drop across it, well, shoving in the probe made it work again, and all of a sudden everything came to life. So I wasn't planning on doing this today, but now I have. I've just moved ahead and done what I'm intending to do, which is to rip out that car audio fuse holder and replace it with this miniature circuit breaker up here, which is a 32 amp one. So in order to do that, I had to mount this piece of DIN rail, which has got room for a couple more breakers, and they'll be added in the future, and make a new lead, which is this one here, this red one, because that original green one wasn't long enough to take this path and link up down here. So it's all hunky-dory now, it's all working, but look how embarrassingly low the amps are now, because while I was getting this part of it all sorted out, the weather's decided to go piss poor again. But that's what happens with solar. But at least now I've got a circuit breaker that I have confidence in, and this is all good. So this will just about be it. I'm just going to do a quick shot of the fuses outside, and then we will wrap it up. Okay, we'll definitely make this quick because the rain has actually come. Here's these crappy car audio fuses. Look, the one I've just taken out today does have a brand name just about perceivable on it. Raptor. Well, let's just call it Craptor, shall we? I bet you this one's the same. Okay, so 5AG fuse, nothing wrong with the fuse itself, just the holder. This side here, this end has become so overheated that it's actually fused the plastic there. That's why it's white instead of blue, and you can't get this bit out. I'll still better get the wire out, but you can't pull this end out of the plastic now. It's sort of stuck in there. Look at that crap. Fortunately, nothing bad became of this, but this is a 30 amp fuse. You know, it wasn't even passing anywhere near the current required to melt this. This one here, even worse. This is the one that came off the lighting inverter, which left us in the dark one night. And look at this fuse, even the fuse has come apart. Like, not blowing, but just fucked out from the heat cycling. It's kind of like melted away in there. This is all, again, all melted and, you know, pieces of shit things. I mean, admittedly, these two fuse holders I didn't buy brand new, but they weren't exactly in completely crap condition when I installed them. Rubbish. Now I've got two more of these left in my system, one on the B bank and one that's fusing the fridge and freezer inverter, but they are American Hi-Fi ones and brand new, so hopefully they'll last alright. It just seems to be when you start opening them up and, you know, using them as the occasional disconnect, they do get a bit sloppier, but I would not recommend these kind of holders, on solar. I probably wouldn't recommend them on car audio either. I mean, if I had a big hi-fi in my car, I don't think I'd trust it to these pieces of poo. Craptor on day 724 off the grid.